Hi everyone, welcome to my videos on elementary differential equations. This is video number 14 for chapter 2. In this video, we will look at the mixing problem. This is a modeling problem, modeling with first order equations, problem type number 3. So these type of problems are word problem, usually comes with a rather long description, and one needs to read each sentence very carefully. Okay, so let's see. So here says at t equals 0, at the beginning of the time, we have a tank, and inside the tank, we have a mixture of salt and water that is Q naught pound of salt dissolved in 100 gallons of water. Now, starting from t equals 0, we are going to pour a mixture of salt and water into the tank. The mixture we pour in will be a quarter pound of salt per gallon of water. That's the mixture. And the rate we pour in will be r gallon per minute. Okay, so the unit for volume is gallon, and the unit for the salt is pound, and the unit for time is minute. And now, assuming the tank has a valve in the bottom, and one can open it, and assume the mixture is well mixed. So all these have meanings, okay? They are being drained from the tank at the same rate as r gallon per minute. So since the inflow rate is the same as the outflow rate, then the volume in the tank will remain constant in time. Okay, two questions are asked. One, we wish to find the amount of salt in the tank at any time t bigger than 0, meaning the amount of salt dissolved in the water. Question 2, if we let the process continue for a long time in the limit as time goes to infinity, what will be the limit amount of salt in the tank? So we call this QL. L stands for the limit. Okay, so in order to solve the problem, we will rely on first order differential equations. So let's set up the model. We let Q of t be our unknown, and Q of t equal to the amount in pound of salt in the tank at time t. And now we aim at set up an equation for this quantity Q. So what will be the rate of change for this Q? That is, how do we determine Q prime of t? Well, we see that two things happen. One is you are pouring in a mixture of salt and water. And then the second thing is you are letting the mixture, well-mixed mixture, to flow out at the same rate. So the rate of the mixture flowing in and out are the same, but the rate of salt being brought in the mixture and the rate of salt that are leaving the tank, they are different. So the change of rate of change for the Q would be the flowing in rate, we call it in rate, and the rate it's flowing out, we call it out rate, and with a subtraction between them. Okay, let's first find the in rate. This is the rate, and the salt is flowing in. And how do we find it? Well, we see that what is the mixture that's being poured in? Well, that is a mixture of a quarter pound of salt per gallon. And at what rate is it going in? Is at rate R. So if we multiply these two quantities, the R rate and the a quarter, and we carry the unit with us, so R will be R gallon per minute times a quarter pound per gallon. And then we see that this gallon on the denominator cancels the gallon in the numerator. What we have will be R times a quarter, which is R over 4, and the unit on the numerator is pound, which here, and in the denominator the unit is minute. So this product gives me the how many pounds of salt per minute is flowing into the tank. So that is exactly the in rate we are looking for. Now we need to find the out rate, but before that we need a quantity. That is, we need to find the concentration of salt of the mixture in the tank at time t, provided that Q of t is the amount of salt in it. That's our quantity. Okay, so that's a simple computation because we have 100 gallon in the tank and we have Q pound of salt, and then the concentration is just the ratio between them. Okay, so now we can use this to compute the out rate, because the problem says the well-mixed mixture, which is the mixture with this concentration, is flowing out with the rate R. So again, with the same argument, carrying the units with us, the product here will give us the rate pound per minute of salt floating out of. Okay, now we are ready to set up the equation. So we know that the rate of change in Q, that's Q prime derivative, equals in rate minus out rate. And we can plug in. The in rate is R over 4. And the out rate is R over 100 times Q of t, which we just derived here. And then this problem also comes with an initial condition. It was given at t equals 0, there are Q naught pound of salt in the container. So we got a initial condition here. Okay, so we recognize this as a linear first order equation with the initial condition, and let's solve it. This would answer the question number 1. Okay, rewrite this into the standard form. Moving this to the left hand side, we get this equation. Here R is just some constant, Q is my unknown, and then by the method of integrating factor I can quickly find the integrating factor, which is just the exponential function, because this is a constant. And once the mu is found, then we can plug it into the formula for the solution. We have done this many times, so I will be a bit brief. So the formula is mu to the negative 1, and the integral of mu times the right hand side, and that's what we have here. So you can work out this integral, which will carry a constant, and then you can distribute this e into both terms, and this is what you will get. Okay, so there is a constant term 25 plus an arbitrary constant c, and then an exponential function with negative exponent of t. And now we can use the initial condition here to find that constant c. So Q of 0, putting in 0, I get 25 plus c times 1, and that shall equal to Q naught. That's the initial condition. Q naught is a given number. So using this relation, we find c is Q naught minus 25. Okay, finally, now plug in the c into the solution, we get the solution of Q of t is 25 here plus c is this number, put it in here, and the exponential function. So this gives us the amount of salt at any time t. So that's the solution. Okay, so for convenience, I repeat the solution here because we will use it to answer the second question. That is, as t goes to infinity, what will be the limit value for q? Which means this ql is the limit of qt as t goes to infinity. And if we look at the expression here, what happens when t goes to infinity? Well, this is a negative number, so this exponential is an exponential decay, and it goes down to 0. And what we have is only the first term, 25. So if you wait a long time, really long, infinitely long, then there will be 25 pounds of salt in the container. Okay, so I would like to comment that the second question actually could be answered even without setting up the equation, finding the solution, or all that. You can just intuitively argue. So we can observe at an intuitive level that as time goes for a long time, then the concentration of the salt in the tank must eventually approach the concentration of the salt in the inflow mixture, right? Which is 1/4. Then that will be the concentration when t is very large. So if that is the concentration, what will be the amount of the salt? Well, that will be the concentration times the volume, which is 25 pounds, as time goes to infinity. So we get the same number, which is not surprising. Okay, so that's all for this example, and let's move on. Okay, let's look at our next example. It's the same setup, except we have different numbers and some slightly different scenario. So we have a tank which has 50 pounds of salt dissolved in 100 gallons of water. And then the tank has a capacity 400 gallons. If you pour more than that, it will overflow. At t equals 0, from t equals 0, we start to pour mixture in it. The mixture is with a concentration 1 pound of salt per gallon. And it's entering with a 4 gallons per minute rate. And then, at the same time, the well-mixed mixture is drained, but at a slower rate, so only 2 gallons per minute. Okay? So the difference from this problem to the previous one is that the rate you pour in volume is bigger than the rate you drain. So as you can imagine, as time grows, the tank will be filled up and it will overflow at some point. Okay, we have 3 questions. 1, the time when it overflows. And 2, amount of salt before overflow at any time before that. And 3, the concentration of salt at the point of overflow. Okay, let's try to answer these questions. And the first one is a simple question. So we have inflow volume 4 gallons per minute is larger than the outflow 2 gallons per minute with the difference of 2 gallons per minute. So how long will it take for us to fill up the tank? Well, the time will be the volume you need to fill it divided by the rate, right? So the volume would be the capacity, which is 400, minus initially you have 100, so you need to fill 300 gallon in it, and you are filling it at 2 gallon per minute. So you do the division and you figure out that the overflowing time is 150 minutes. Okay, so question 2, we want the amount of salt for t less than the overflowing time. Here we need to set up our model. So let Q of t be the amount of salt in the tank at t before overflowing. And the equation will be set up in a similar way by computing the in rate and the out rate and put them in the differential equation. So the in rate would be the concentration multiplied by the rate. We are familiar with that concept. So 1/4 times 4 is exactly 1 pound of salt per minute. Now we need to compute the out rate. So again, at time t, the out rate would be the concentration times the rate. So 2 gallon per minute is the rate. And we need to find out the concentration of salt. So per previous discussion, we know the concentration would be the amount of salt over the volume of the liquid. So the amount of salt is our unknown Qt. What will be the volume of the liquid at that time? Well, we know initially it's 100, and then at every unit of time you are adding 2 gallon. So at time t, the amount of liquid increased will be 2 times t, and then put this on top of 100, that will be the volume. Okay, so it's this ratio. So this is a bit more complicated than the previous example. Okay, and then you can simplify a little bit, multiply this by 2, so we'll get 50 plus t in the denominator. Okay, now we can set up our equation. Q prime equal to in rate, which is 1, minus out rate, which is here. Okay, so we see that again, this is a linear equation. Let's write it in the standard form. That is, we'll move this to the left-hand side. Then we have this equation here, where this is the P and this is the G per our formula. And the equation comes with initial condition. So we know that initially there are 50 pounds of salt in the tank. Okay, we can solve this equation now with our integrating factor. So finding the integrating factor, exponential of the integral of this p here, and then one just needs to work out this integral, which is a natural log, and then exponential and log cancel each other. We get this for mu. And then once the factor is found, we put it into the formulas for the solution is 1 over mu, mu's here, and then we need to integrate mu times the right hand side g, which is 1, so just mu here. And this is just a polynomial, it's easy to integrate. 50 gives you 50t, t gives you half t squared, and don't forget the constant. And then we need to find the constant using the initial condition, as always. Putting t equals 0, 0, 0, I get c, and I get 50. So c over 50, and that shall be 50. This gives us c is 2,500. Okay, we can now plug the c value in. The c value, we put it in, and we can write out our solution, Q of t, which answers the question number 2. Okay, now we can answer question number 3, since we have the function Q of t, and we know the time when it overflows is t equal 150. So to compute the concentration of salt, would be equal to the amount of salt divided by the volume. Okay, and then Q expression, in the Q expression, set T to be 150, which I put it in here. And you can work out and simplify, and you get 17/64 pound per gallon. Okay, and that's all I have to say for this example. So just would like to give some comments. So in this example, we used a mixture of salt, of water in a tank, flows in and out, and these, you can think of them as an abstract concept. Just if you have a phenomenon, something is flowing in and something is flowing out. It doesn't have to be salt or water. And then you can set up your differential equation in a similar way as we did here for these two examples. Okay, that's all for this video, and next time we will look at one more type of modeling. Okay, hope you enjoyed this, and I'll see you next time.